Well, here we go with what I would say arguably is the most important theorem on all of statistics, called the central limit theorem. Sorry, I kind of went through it there, but central, AL, limit theorem. And the basic idea is this. Now remember, as we've been going through things, we have this original distribution called the parent population, and it has some shape. I don't know, binomial, something, I don't know. It looks like that. If I take a sample, or maybe multiple times, I take multiple samples and I graph those. Each of those graphs will look, depending on how big, will look similar. If I make like a dot plot of the different sample pieces that I get, it'll probably look similar to the original parent population. But this is the distribution. Each of these are called sample distributions, or distributions of samples. And then if there was something that I measure from each of these samples, so maybe for each of these I find the standard deviation. Sample statistic, remember up here we have mu and sigma parameters, and then I take all of these and I plot them all on the same graph. And I plot all of these S's on a graph. All right, this is called a sampling distribution. Okay, that all being said, what the central limit theorem tells me is that if I have a sample of size n, sample size is n, as n gets larger, the sampling distribution, approaches a normal curve. Okay, so what does that mean? It means, let's take a look. Go to here. So here I am back at this applet again, which we've used before. And I have this distribution here. This is just one I made up. All right, so now let's go down here. If I do 5 samples, let's animate one. It takes 5 data points, or sorry, 2 data points, then graphs the mean. 2 data points, graphs the mean. It says mean and 2 data points. Do this 10,000 times. I look at this distribution and say, is this approaching a normal curve? No way. All right, it notices that a lot of data comes from here. Sometimes it comes from here. Sometimes they both come from here. Sometimes they both come from here. So I get this like trimodal looking thing. All right, but as my sample size gets larger, so now I have 5, 2 and 5, animated 10,000 times. This still looks about like the last one did. But this bottom graph, you're like, oh, it's looking more mound-shaped. All right, but it's still definitely left skewed, because you can see that left skew to it. It's got this weird super top thing going on. So what if I go 5, and I do the mean again, and I compare that with 10? All right, here it's still that same kind of flat toppy thing and skewed to the left, but this now is getting more normal, actually approaching very closely to what would be a normal curve. And that's only with n equals 10. Now I shouldn't say what we're going to find, what I'm going to tell you is this. Okay, regardless of population distribution, or shape. So when I say distribution, I'm really talking about regardless of the shape of the parent distribution, whether it's really, really strongly skewed, or it's bimodal, or maybe it's just completely unknown. All right, if my sample size n is at least 30, then the sampling distribution is Close enough for us to say it's approximately normal. All right, the sampling distribution will be centered at mu sub x bar, and will have a standard deviation of sigma sub x bar. All right, this equals the original mu of my original parent distribution, and this will equal sigma over the square root of n, so over the square root of sample size. And that means anytime it's over 30, doesn't matter how far, it could be 30, could be 29, could be 50. Now this is dealing with measurable data, because we're talking about x bar. So you say, well, what about proportions? For proportions, we have to think about a couple things. Now, in both of these cases, we always have to assume SRS. Always have to assume these are coming from a simple random sample. And this includes X bar. All right, 2, independence. We said if the sample, let's go with this. If the population is 10 times larger than the sample, then picking one thing out of the population does not influence the likelihood of picking another thing out of the population, so we say then it's independent. All right, once we know independence, the standard deviation of p hat, because these are proportions, so remember in proportions, if we're talking about the population value, we use the letter p, lowercase p, sometimes capital letter pi. And if we're talking about a sample, we take a proportion from a sample, it's p hat. So the standard deviation of p hat will equal pq over n square root of the whole thing. Third item, and this is the biggie here. If np is greater than or equal to 10, and nq is greater than or equal to 10, then if those two things are both true, so if that is true, therefore sampling distribution of p hat is normal. And that's a big deal. All right, that's a big deal. All right, so I had two things there. So when I was measuring, again, got to assume simple random sample. Got to assume in the original one that picking one person out of a sample, sorry, my population is 10 times larger than my sample size, therefore independent. And then the third thing for X bar was that if n is greater than 30, then the sampling distribution is normal. So we've got a couple things going on here. For X bar and for p hat. Normal. In order to be normal, if parent population is normal, then sampling, always have that ing on there, distribution of X bar is normal. 2, so what if we don't know this first one? Then the second one, if n is at least 30, then sampling distribution is normal. Over here for p hat, we've only got one thing. NP is at least 10, and Q is at least 10. Sample size times P, sample size times Q. Over here in red, I'm going to write this. Is irrelevant. And people will try to use this all the time. They'll say, oh, my sample size is over 30. When I did a sample poll of 150 people to see if it was a yes or no question, that's a proportion, not a measurement. Cannot use this. All right. So again, central limit theorem says as n gets larger, the sampling distribution will become approximately normal. All right. The larger n is over here, n times p will get larger and get closer to 10. Over here, as n becomes larger, or actually once it gets to 30 or more, the sampling distribution is normal. So then, the last thing we can do is, we can then say, well, what happens if I have this sample size of, let's see, 32, let's say I do that and I get an X bar of, let's say we're talking about, going back to that like pregnancy length, 267. All right. From that pregnancy problem that we did, 266 was the average number of days. The standard deviation of the original population was 16. All right. We could probably calculate out what's the probability that just one person has a pregnancy that lasts longer than 267 days. Now this came from a problem, and we knew that the parent distribution was normal. So we say, okay, this is 266. There's 267. I do z equals 267 minus 266 divided by 16. Now what happens over here is I have a different distribution, still centered at 266, but my standard deviation is now, because these are x bars, because I'm talking about the average x bar here, sigma sub x bar is equal to sigma over the square root of n, which is 16 over the square root of 32, which is a smaller number. So now 267 is over here. So I go z equals 266 minus 267. Sorry, other way around. It's x minus mu. Come on, people, correct me. 67 minus 66, I had it right on this side, divided by 16 over the square root of 32. In the reflection response, I want you to find that z-score and then find the corresponding probability, right, 0 there, whatever that z-score is. Find the corresponding probability that x bar is greater than 267. It should be a much lower probability than this one over here, because for one data point to be over 267, not that uncommon, but to have 32 people with an average over 267, that's actually a lot different. All right, so that's what I want you to do, and fill that out in your reflection response, and we'll see you in class.